Okay, this is, as it says, the motor effect, as it called at GCSE. More correctly, it's the force on a current carrying conductor, which is hard to say. So section 2 of the electromagnetism topic, it's definitely all about the field and the forces. So again, sticking with the ideas that are similar to electric fields and gravitational fields. Now the difference is that this is very much about usage. So the applications, the way that you can use this is one of the bases of which we base most of our modern world upon. If you think about it, most of our world runs on electricity, and electricity only has three effects. One of which is it causes things to heat up. Okay, that resistance causes heating, used in lighting, not very effective, and in heaters and so on, kettles. It causes a chemical effect that can be useful for some things, and the third thing is it creates a magnetic effect. So this magnetic effect on other magnets is really, really important. All of them work on the basic principles from section 1. If you have two magnets, they will attract, or if you spin one around, they will repel. Okay, I won't show you them here, there's not a lot to see, but if you play with them it's very obvious, so we'll try and get some hands on. Now we can build up to this, and a lot of people don't really get confused, get a little bit confused with what's going on here. We will come to the mathematics of this today, but there's a basic background effect, and again I would demonstrate this, but it comes down to hand rules. So we are today going to introduce the second hand rule, which is came upon by Mr. Fleming, as compared to the grip rule. So we're going to use both hands today, and that will help what's going on, but I'll bring in analogies as well. So this is actually one of the required practicals. It was also at GCSE, we just need to add on a little bit of detail to it, that's all. So it's a slightly higher level, there's a bit more to it than what you think, that's all. So in the notes, we'll go into it. If in the ideal world we manage to get the practicals done when we come back from lockdown, then that will help. But again, it's a shortish section of notes and based on the key ideas, so keep thinking about those simple ideas. Okay, now what we are always going to do, as I said, is have two magnets, but this is forming your second magnet. So all that stuff from the first section is really crucial, just the idea of it, not the mathematics, but the fact that if you have a magnetic field created by electricity, then it is temporary, it is variable. Okay, and that makes things very obviously important. If you want your car to go one speed, then you only need one strength of magnet, but if you want it to change speed, or slow, or stop, then we need to be able to change that electric current. Okay, so a lot of it's based around that principle, but yeah, this is where actually this comes into most useful, because if you try and make an electromagnet with a long, thin magnetic coil, okay, the solenoid, well, it wouldn't spin. Okay, so not much good. We use this for static magnets very commonly. We will use it to create MRI scans. We will use it to magnetize you by shoving you inside a long tube with a very, very strong electromagnetic field around it. Okay, so we can use that in a big way for many useful magnetic machines. What we're going to do here is actually just look at the idea of forces being created. Now, I will pick up, because I've mentioned MRI, the basis of this that we didn't really discuss last lesson is that on its own creates magnetism, but how do we actually magnetize certain materials? So if we stick a core in, how does it work? Well, soft materials, imagine this was a bar of metal. If this was a hard material, it'd be very hard to actually get the magnetism in this to create a magnetic field. It'd be very hard to magnetize. But once you've magnetized it, it stays magnetic. So if we pick up a bar magnet, that picks up iron filings and things, then that will be made of a hard material like steel. If we go into a soft material, then basically if I chop this in half, I end up with, instead of one magnet, I'm going to end up with two magnets, and they will still have a north end and a south end, etc. And I can keep chopping those smaller and smaller and smaller and smaller, and they'll always still end up with north and south ends. It doesn't matter how I break it up. And obviously now we know, since this theory came in many years ago, we now know about atoms. So what we actually know is what's happening inside depends on the atoms in the material. And some are very easy to magnetize or use their magnetism to move them around, and others aren't. So that's where we get these hard and soft materials. So if we look inside, basically everything has tiny little magnets all over the place. Here's my north and south poles, for example. Think of it as compass points, pointing in different directions. Now the material I'm drawing here isn't at the moment magnetic, but of course it is. Look, I've got all these magnets. However, all these magnets are cancelling each other out. Okay, so this is known as domain theory. If we chop everything up into its smallest domains, each one acts as a little magnet. And in materials that are hard to magnetize, these actually are very difficult to move around, okay, change the orientation of them. Now really what's happening is we have our nucleons, okay, our nucleus as a whole, it spins, okay, and as it spins it creates a magnetic field, very much like current flowing around a coil creating a magnetic field. Now it's not that simple. It's quantum mechanics, and it's not a 360-degree spin and stuff. It's a bit more complicated. Basically all of these are a bit like spinning tops. What you can do is get them to go over at different angles, okay, and some of them are easy to move, some of them are hard to move. If they're easy to move, then if you put another magnet near it, for example like that, what you'll end up with is that some of these, particularly ones at one end, but actually those ones will then affect the next one along, and the next one and the next one, you'll end up with basically these all kind of lining up, or maybe some of them, not all of them, but overall your bar becomes more magnetic. And depending what you do, especially if you wrap it in a coil, then all of these can end up being lined up, okay, and now all of the little magnetic fields from all of these domains lines up to create one big magnetic field. So you have created magnetism. Okay, so this is called mutual inductance. You're inducting magnetism. However, when you take that away, if this is a soft material, then these will actually start to spin back. Our little tops will start wobbling, shall we say, and they all point in different directions. So it's very easy to demagnetize. It demagnetizes itself. Now we can do this with you. Hydrogen ions are very easy to magnetize, and your body contains a lot of hydrogen ions. So if we stick you inside a big solenoid, we can get all those little magnets lined up. Okay, so if we put you inside a big magnet, as in a strong magnet and physically big enough obviously to fit you down the middle, if you sit you into an MRI machine, the magnetic field will line up all your nuclei, okay, or a lot of them. So really what you should see on scans is NMRI scans, nuclear magnetic resonance imaging, but people get upset when you say nuclear, even though it's talking about the nucleus of an atom. Hey ho. So MRI scans in hospitals, and again you can do this with chemicals as well, as the chemists will be aware of. So what happens in bodies is that when you turn this off, there we go, we create our magnetic field, great, and we have our big, let's say that end is our B field coming that way, so we can line up all the magnets inside. When we turn it off, what happens is these will all spin back, but they'll all spin back at different rates, depending if they're in fat, connective tissue, muscle, etc., liquid in the body. And by timing how long it takes for them to turn back, when they do so, they create a little current. They do it in reverse. Instead of current making magnetism, magnetism changing makes current. We induce current in the wire, and we can measure those spikes of electricity as it flows out. And by measuring the different times of the spikes with a computer, we can build up computer models, which gives you those lovely MRI scans of your body, the soft tissue in your body, because they have to be able to move quite easily. So that idea is what gives us the big magnetic fields. It's what you put in the middle. So when we look at things like motors, which has now just started to rub off, what you put here is important. This is the core of your coil. Okay, so here the coil with the electricity flowing, okay, and we'll just put it there because it's there's an in and out, but there's some clever stuff that goes on for those that have done this at GCSE. We'll know about it depending if it's an AC or a DC motor, etc. But that makes a very strong magnet. Here we have a permanent magnet made out of hard material, hard magnetic material. So this is staying magnetic. Modern day it tends to be ceramics because they actually, we can design them to work well. But this creates a magnetic field. Here we have a magnet. You put the two magnetic fields together and they will repel off each other. Okay, and that is the principle of the whole of this chapter, or this section of the chapter, on magnetic forces. Okay, so forces between two magnetic fields, one of which is controllable. Okay, now we can put these together and we can kind of think about the fields and try and work it out. It's quite hard when you start adding up all the sections of field, but basically here's our circular things around our wire. Here's our permanent magnet, north to south. So they're in top of each other. When we move that into the position in the middle, well, some of them, if they're flowing in the same direction, will create more lines. So we're ending up with more magnetic field lines, flux lines above. And underneath, we've got ones opposing each other. So they'll cancel each other out and make it weaker. And you can think about that deeply, or go back to the simpler way, think of these like elastic. These have all been stretched. There's only a little piece being stretched over here, so basically this will get pushed down. Okay, so think of elastic shortening is a really powerful idea. In terms of how we think of that, more so over the page a second, we have a hand that will will be very helpful for us, and that is our left hand rule. Okay, come back to that in a second. However, GCSE, you did a piece of work on this, which gave you an equation. Okay, it was in one of the equations that was given to you, and we're going to use that. Again, it's one of our really useful equations. It's probably the first one for this chapter. These are just in the background to keep you remembering it. Okay, how do you turn up the speed of a motor, for example? More magnetism, we need more current, logical stuff like that. So their background, but our first proper equation comes from this, and we will find it here, but it's not quite obviously as simple as what you get at GCSE. So, crucial things, it depends on lengths. When we do this practical, there's different ways of doing it. We could stick a wire in between our magnets, just like we have with the motor. So rather than the coil, just stick a great big wire through the middle with electricity, and what you'll find is that gets repelled upwards or downwards, depending on which way round the north and south is, depending on which way the current is flowing. But also it depends on the orientation. So if we change the angle of this, we'll actually get bigger or smaller forces. Now in our practical, and I guess you did this at GCSE for the required practical for everyone, not just triple award, separate sciences, what you can do is measure the size of the force using a top pound balance. Okay, of course it gives you the mass, the apparent mass, but actually if you multiply it by G you get the force, because actually that is measuring force and it just converts it to mass, so you convert it back. Okay, so the basic idea is we can do some experimentation on it. We can change the angle of the magnets, we can change the length of the wire that's in the magnetic field, etc. Okay, so it seems a bit odd, but it actually is quite possible to do. How we describe it is this. Now be very wary if you look on Japanese websites, which a lot of people seem to pick up on, because they've got some great animations. They use different letters. Okay, they use different way. They use it in a completely different way. But if you think of what you're trying to represent, you have some electric current flowing. So we use the second finger for the current. Bear with us. That sounds a bit odd, but it does work. Second finger for current. Our first finger is the field. Okay, so that's more obvious. And F. Doesn't really, I don't like the F. Let's cross that out. Let's say thumb for thrust. Okay, or some people prefer thumb for motion. Either or, doesn't really matter. Okay, but this is what you start with. The finger, first finger and second finger. What it produces is a force. Now, at GCSE, they were all at perfectly at 90 degrees to each other. So that is 90 degrees to that, that is 90 degrees to that, and this is also 90 degrees to the thumb, which I will not attempt to draw. Okay, so they are all perpendicular. So forces work best when they're perpendicular. If you reduce the angle between your current and your field, then imagine it a bit like an umbrella. If you close two of the spines, the third one comes down. It doesn't change direction, but what it does is it shrinks. So the smaller you make those angles between the current and the field, you'll find the smaller your force gets. Okay, so it's a nice kind of little link, and very importantly, you can work out what's going on again in the exam by doing this. So, because I haven't got it in the notes so well, I have drawn on some forces. So here is my force arrows. So this side is going to get pushed up. So let's just keep that simple. Ignore the near side. If that is going up, and this is a north pole here, so I've got my magnetism flowing in that direction. There's my B, okay, all the way across. Okay. Which direction is the current flowing along this far side? Well, get your hand in. Okay, now again, like in the exam, that's not very convenient. So I have the field going up. Okay, I can do that. Bit awkward, so I'm going to turn it around. Do this in the exam. My field is going up. Sorry, my field is going up. My motion is going up. The force, my thrust, my motion is going up. My field now lines up with my arrows. Okay, so that's good, which means that the current is flowing out of the page. Okay, so for this to work, what I need is current where the force is being produced is flowing in that direction. Okay. We can double check that because motors tend to spin round, because one side gets flipped up and the other side gets flipped down. Does that still work? How does that still work? Well, of course, the current is flowing around, so the current's flowing this way down this side, and therefore it must be flowing that way up that side. Okay, so again, there's our current. Excuse me, that's a bit rubbish. So there's my current flowing round in that direction. Okay, so if I again check that, this is going to be awkward. I'm definitely going to move it around. So my second finger is going in the direction of the current. My first is in the wrong direction, so I'm going to have to change that. So first finger, a bit hard to see on the video, I know, it's going across. My second finger is going along that, which means that yes, my thumb is pushing downwards. Again, it's a bit easier not trying to show it on a video. So yeah, it all kind of agrees. Swap the direction of the current, same direction of the field. You must therefore swap the direction of the force. Okay, so it all comes out with this left-hand rule. You just need to make sure you remember which one is which, because if you swap them around, you'll get the opposite effect. If you are manipulative with your hand, you can try this. Don't know how well this is going to work. If you swap the direction of the current, field goes down, but you swap your direction of the field as well, then it still goes up. So actually, the effect will be the same if you've got the field going that way and current that way, but if you swap both of those around, it still goes up. So if you swap one, you'll swap the direction, but if you swap both of those, then you still end up with the same effect. You kind of swap it twice. Alright, so yeah, have a play with that. Now, in the data book, you don't get the GCSE equation, and that is for when the wire is perfectly perpendicular. So the simple version is F equals BIL. Excuse me, that's not a B. BIL. Where L is the length of wire that is in the magnetic field. Okay, so it's where they cross over, it's where they're actually in contact with each other, shall we say. So it's not the length of the wire. You can have 4 meters of wire, but if it's only going through a section of magnetism that big, it's that length of wire that matters. Okay? Current, fairly obviously. Field strength or flux density is obvious as well. If we change that, then it will get smaller. So if we measure the angle, okay, and again, just use some common sense, depending which angle they label, they should do the one that therefore gives the data book value, but basically the force will get smaller. So what they're doing is when it's at 90 degrees to the field, so maximum at 90, therefore if you have the sine of the angle, as the angle gets smaller, that value gets smaller. Okay, so the version in the data book is BIL sine theta. Now, it's a quick one to check. The force is the old bill. It used to be quite a common phrase in the 70s and so on. Might kind of work. So force, old bill, etc. Now, this also, I should say, gives us the definition of what that unit is. Okay, so like we had the force and the field strength or electric field multiplied by charge, or gravitational field strength times by our test mass will give us the force. We have the same equivalent idea. Force and field strength, although it's called flux density here, field strength times by some multiplying factor. So this thing here, I times L, is how much current flows through certain length, is known as a current element. It's beyond the course, but it's an exact equivalent. Okay, so what that means is that 1 Tesla is when you get 1 Newton per amp meter. Okay, and that, with a little bit more detail obviously, is the definition for 1 amp. So when you look at SI units, how they define the amp is in terms of forces. Okay, 2 wires, parallel, infinitely long. Yeah, if you put them 1 meter apart and they're a certain length, blah, 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 you'll get a size, a force of 1 Newton. Okay, because it will make everything 1 in the equation. So that's worth going and looking up. You can get the full details. I can't quite remember it because there's streams. There's a pi in there and stuff like that. So what it does is it relates us to that kind of same layout where we've got, if we talk about force gravitational field, it's test mass times by G. Okay, force of an electric field, excuse me, should be an F with an E subscript. Force of an electric field is that idea of a test charge times by electric field strength. Okay, so that's our field there, and for this one, the force on a magnet, so we use B, is going to be that that IL, tends to be a little l, times by B. Okay, so that's our idea. It has that kind of equivalence. Having something in that field will produce a force. So the closest thing we can get to a test mass or a test charge is actually putting an electric wire within the magnetic field. Okay, 1 amp flowing along 1 meter in a magnetic field, if you could make magnets that big. Okay, kind of difficult. Now we will do a little bit on this. It's not actually on the spec, it's the idea of what's in the spec. Okay, they can ask about loudspeakers, and again it's describing what's happened, so it's all actually about the description of this. So you know, the idea again from section 1, that if you have a magnet and you put an electric magnet near it, then that electric current, the magnetism it produces, the magnetic field it produces, will repel from the permanent magnetic field at right angles. So all of that comes together as actually a description to explain how anything magnetic, any magnetic machine, sorry, works. Whether it's a moving coil meter, you know, one of those dial ammeters. Let me just grab one off my side. There we go. So there's a moving coil meter. If we look inside there, can't quite get the light on it, but there's our coil, okay, running across there. This is a motor. It's just that it doesn't let it spin all the way. It has springs on to stop it rotating and to give it a nice linear scale. Hooke's law and all that. So yeah, they all work in the same. Meters, motors, loudspeakers, microphones, which is actually a loudspeaker in reverse, and things like that. Okay, so they're all based on the same principle. However, the most obvious one is a motor. So a little bit beyond the spec, but just so we can see what's going on. Now, if you did this at GCSE, the difference between this and this is that because it doesn't turn a full way round like a motor needs to, you don't need to have any special connections. We have 2 connections, they're permanently connected to the coil, it moves and it will flex. Okay, with a motor you obviously need it to spin. Okay, and there's a great website I'll put the link on for University of New South Wales in Australia, and they have some great animations so you can see how motors work, different motors work. The simplest is a DC motor or a simple AC motor, where you just have basically what I drew. Curved faces help, we'll show why in a second, and actually if we can curve the faces around more, that helps. Or more usually what we have is actually multiple coils at different angles to each other. So we'll have a flat coil there, we'll have a second coil at a bit of an angle there, a third coil at a bit of an angle there, etc. However, the problem with these, and if you have anything like, I know, Aurora or Scalextric's cars and things like that, you'll get a lovely smell from them because you get sparking. Okay, so it's really bad to have sparking, it pits the contacts, but you have what's called a half ring or split ring commutator here. Don't worry about that. Again, GCSE, sorry if it brings back bad memories. But yeah, you have a way of swapping electricity as it goes in the coil. Come back to that in a bit with this. But you get sparks every time it flips over. So most motors, motors in industry now, for them to work smoothly, work on AC, alternating current. And that doesn't need this. You just need smooth, constant contacts, and so you don't get sparking, you don't get those effects. Now, if you go on London Underground, you'll hear some of that induction motors kicking in. It's actually creating magnetism, and the connections are much simpler, and it doesn't break down and stuff like this. There's little simple electric motors, they don't last forever because of the sparking. Okay, so different connections depending on what type of motor and what type of electricity it's running off, but otherwise the principle is the same. North and south pole north and south permanent magnet, and a temporary electric magnet in the middle. Okay, so how's it work? Well, let me just move those pages out of the way. There we go. So what we've got is each side experiences a force. Okay, so F equals BIL. Now this would be a bit of a rubbish motor. How do we make it better? More coils. So if we take the force acting on each side, there's the length. Okay, so the length is along there. The current is fairly obviously flowing around all the way around. And B is the magnetic field strength of the permanent magnet. Okay, so again, just put up here, it might be worth thinking about, that's your permanent magnet, usually. And when I say usually, it will be for all questions that you'll get, but for real life it's usually a permanent magnet, and this is your temporary magnet, your electromagnet. Okay, so temporary electromagnet. So if we put that coil, that electromagnet, inside your magnetic field, and we put more turns on, then we fairly simply have there's a lot of space here to write, not very much, BIL times by N. Okay, because each one will experience a force. If we've got two coils, it'll get twice the force, you'll get twice the acceleration, force, acceleration, movement, yeah? Now, the clever bit about this is that, or the bad thing about this, is that the angle changes. So if you just have straight magnets, the force will always be perpendicular. And what you actually want is the force to change as you go around. Okay, you want it to keep turning, the force turning around rather than being at an angle. Now cast your minds back. This is simply everyone's favourite topic from the beginning of year one. This is moments. Okay, so what we had for our definition of moments was we needed the distance from the pivot and the perpendicular force. Yeah, so for this to work, and again if we have a couple, okay, so two forces that are providing the same effect, they're adding together to do the same thing, then our force on each side will give us a moment. So my total moment is force times distance from the pivot. Okay, so FD plus, on the other side, same force, same distance. Why? Because our motor has the pivot in the middle, both have the same number of coils, both are the same length, so therefore that's going to be equal to BIL. Okay, so what we can do is use moments from last year to do it. However, it comes to this, our force is pushed upwards, and if we have our magnetic field coming in always from that direction, then this will only get pushed upwards, it won't get pushed round, it will not stay perpendicular. So one way of getting around that is actually, instead of, let's bring it into shot, instead of having magnets that look like that, we can actually make them curved faces. So what happens is those curved faces will actually create a field that squashes in. Our field, don't forget our coil edges are going to be here, so we're not worried about the bit in the middle. We'll come back to that in the lesson with the PowerPoints. We can go further than this as well, but basically the field is coming in and is perpendicular to the surface. So it can spin round and the force will always be turning it around, will always be perpendicular until you run out of magnet. So the more we can curl that around, the better. Obviously if they touch, nothing like electricity, nothing will go across the gap, it will go the easy way. Or the majority will flow through there. So yeah, curved surfaces on magnets work really, really well, or lots of north and south poles. You make a compound motor with lots of different coils and lots of different magnets. But let's keep it simple because each magnet does the same thing. So if we think about the linking torque, in other words, a couple, the force of a couple, then what we end up with, as it says from there, we end up with the force. I don't know if you remember the equation. If not, it's on your data sheet. The force on each time multiplied by the diameter d. Okay, so in my diagram here, perhaps I should make that radius because it's a circle. So my radius, in which case radius equals 2 lots of fr, and 2 radii is of course diameter. Okay, so that's where our equation comes from. We did it last year. I know it was a long time ago. It was September when we did it. Okay, so a year and a half ago-ish. So if we take that, as I said, we can link that. That's 2 lots of f times radius. So that might work better for you. Okay, just to show where it's coming from. So here is our central axis. Okay, through here, and that is our radius from there to there. Okay, there is our length. Again, I can't really label that from this diagram, but that's our radius for it. Now, obviously we have force there, so I can just combine them to give me the whole thing. So my turning effect, my total turning effect, the torque is 2 lots of B I L times N times R. Okay, but we can examine this a little bit. If I've got 2 lots of radius, okay, so in other words I got that length and I've got that length, and I am multiplying those together, so 2R times L equals the area. Okay, so what I can end up with is I can simplify the equation just based on the area of this coil, which interestingly means that I will still get the same torque from the motor. I will still get my same, for example, acceleration of my car, whether I have a short but wide motor or a long thin motor. As long as I have the area the same, I will still get the same torque from it. Okay, so if we put that in, we end up with a really nice little equation, which is the torque equals Bn. I'll put it that way around because it sounds humorous. Okay, so magnetic Ian. So if we put those together, that really works. But it is worth pointing out, if or when, let's put it here, if the field is 90 degrees. You usually think of the core actually, but there we go. The field is 90 degrees to the motion. Okay, and if you were doing, for example, AQA, you go much further depth. So as the angle changes, that angle there, then what you'll find is you need to bring in a multiplying factor so it reduces, etc., etc. So again, you're just multiplying up by trigonometry. You're just finding components of the forces. Okay, but a nice little kind of idea. Think that through. You know, that is the full, pretty much the full mathematics. Okay, with cos theta thrown in there for all types of electric motors. Okay, which we don't study, but actually it's just coming back to that equation. That's the force on a single current carrying conductor. Go back to first lesson and you just remember that we can get more magnetism if we have more coils or more current. So again, use your logic to how do you make the forces bigger. But key point from today, it's biggest when they're all at 90 degrees to each other. Okay, seem to have ink on my hand. Okay, so I have slotted that in right at the bottom, max perpendicular. So keep coming back to that. And what we can do is, as I said, I'll just put in that little bit of a footnote. I have got it scribbled somewhere, but I thought I'd caught this out. We can put it in any other position. Torque is reduced by a factor of cos phi. You will not need that, but that's just to link it in with that labelling on the diagram. It's the best diagram I could find. Okay, so we're going to stop it there. Everything keeps coming back to the top half of that, really just this and the exploration, the investigation that you need to do as required practical. We may have to do another one because you know the answer. There we go. Yeah, so we'll leave that. That on its own doesn't tend to come up. This idea on force on a current carrying wire, other than things like multiple choice questions. Okay, what most of them do is not thinking about the wire, a wire being forced around. It tends to be individual little charges. Okay, so single electrons flying through a magnetic field rather than big wires.